So good morning, everyone. My name is Jose Torralba. I am going to present this paper, which is the title is Review of State-of-the-Art of New Opportunities for Powder Metallurgy for Hydropialoids. This work has been made with the collaboration of Pablo Alvaredo, also from the University Carlos III of Madrid, and Andrea García Gunceda from the India Materials Institute. So this will be a brief review because we don't have so much time. But I will try to introduce in these 20 minutes just the most important, let's say, things that I consider could be interesting for you to be introduced in this world. So we have to take into account that for more than 7,000 years, all the alloys that has been used by the human being is an alloy in which you have one metal as host for other metals, which are the alloying elements that are used to improve possible weakness of this base metal. It happens also including the superalloys, in which we have also a main host metals and then other alloying elements. Only in the 70s, where the intermetallics were introduced, we had some different alloys in which we have more than one main host metal. In that case, usually we have two, or even usually two different metals. But in 2004, there were two papers published, one by Cantor and collaborators, and the other one by Ye and a collaborator, in which they develop a new concept of alloy. Is the concept of high entropy alloys. In this concept, they demonstrate that if you mix 5 elements in equiatomic proportions, you can have, in some conditions, one single phase. That means that you don't have, as could be expected, intermetallics, or you can have precipitates or different brittle particles, brittle phases inside the main structure. So what they do is to demonstrate that in these different alloys, the conventional rule of the Hume-Rothery rules in order to predict the possible solid solutions is another completely different matter. In that case, you have a high entropy or entropy of mixing and a reduced atomic size, you can be in this area of this graph in which you can expect for those alloys a solid solution. Later, I will explain a little bit more about these conditions, but if you fulfill these two conditions, a high entropy or entropy of mixing and a low atomic size, you can be in this square in which you can have only one single phase. So even if you consider other conditions like the valence electron concentration, even you can predict if this single phase is a BCC or FCC. Most of the hydropialoids belonging to the transition metals are usually FCC and sometimes FCC plus BCC, and the refractory metals used to be in the BCC corner. So the interest for the hydropialoids has been increasing in the last years strongly. If you consider that in 2004 there were just those papers above mentioned by Ye and Cantor, and it was growing from 2005 till 2012, having in the order of 50 papers per year. Today, we expect for 2020 more than 1,200, maybe 1,300. Last year, in 2019, we had published more than 1,000 papers on high entropy alloys. From those, in the order of 110 in 2019 were papers devoted to high entropy alloys and powder metallurgy. And from those 110, in the order of 16 were papers related to powder metallurgy, but materials developed by additive manufacturing. So additive manufacturing is also a group of materials, high entropy alloys produced by additive manufacturing that are having an interest, increasing interest in the last years also. So if we see where those papers were published in general regarding high entropy alloys, I think we can contemplate 3 main blocks. One block is United States, other important block, the main one is China, and if we consider all the European Union together, we have a similar response than United States. So I think in Europe we are working in the same level than United States. But HEA established different requirements to be considered for one alloy to be considered as a high entropy alloy. We have 4 different effects that have to be fulfilled to be considered as high entropy alloys. We have thermodynamics effects, the high entropic effect that I mentioned before. We have the so-called sluggish diffusion. In order that it's not a fast diffusion to reach to the alloy. We have a very severe lattice distortion that will improve the properties. And we have a lot of cocktail effects because we are using different elements from different characteristics. If we consider the conventional ingot metallurgy high entropy alloys, we can classify it especially in 2 main groups. One group is the so-called 3D transition metals. Other group is the refractory metals. So we have this kind of high entropy alloys and these other different refractory high entropy alloys. And there are another 2 groups in which some like metal materials like aluminum or titanium are included. Most of these high entropy alloys are small variations from those. One typical example is the Cantor alloy. We will talk about the Cantor alloy later. There is a lot of possibilities replacing one element from the Cantor alloy by aluminum or titanium. And we have also the so-called lanthanide high entropy alloys. But if we collect only the papers published on powder metallurgy and high entropy alloys, those 110, 120 papers, we can classify mostly in 2 groups, refractory metals and transition metals. In the transition metals, we have this group in which we have in the middle the Cantor alloy with nickel, copper, iron, chromium, and manganese, and some other high entropy alloys in which we have replaced some of the elements of the Cantor alloy by other elements. The addition of aluminum and other elements can produce the movement from the FCC phase to the BCC phase, and in the case of refractory metals, most of them present the BCC phase, a single phase. How we can produce by powder metallurgy the high entropy alloys? If we analyze the literature, 76% of the papers reflect the mechanical alloy production of the powder as the main way. Then we have a small amount of 13% of gas atomization, and some other papers, they use mix of powders to develop the high entropy alloy. When we use mechanical alloying, most of the times, the consolidation method that we use to produce the final part is spark plasma sintering, and sometimes hot pressing, conventional hot pressing or hot isostatic pressing. But most of the times in the papers are used spark plasma sintering. At the end, sometimes we have to produce an annealing process in order to control better the microstructure, control better the final microstructure. By using elemental powders, we can also using conventional uniaxial pressing or cold isostatic pressing, followed by sintering. It's interesting to analyze the mechanical alloying process in the high entropy alloys. If we are using just metals, we expect, in principle, a behavior that was described by Benjamin many years ago, in which we have an evolution of the powders in the so-called ductile mechanism, in which we have the starting powders, a flattening of the particles, welding, fracture, and then welding again, and then we reach the steady state. On the opposite side, we have the so-called brittle ductile mechanism, when you have brittle particles and ductile particles, and the evolution of the final particles follows these different steps. In high entropy alloys, there is a very interesting paper published by Rasa and collaborators, in which they demonstrate that the mechanism that is followed is the ductile brittle, not the ductile, because when we mix 5 elements, like in that case, chromium, vanadium, manganese, moly, or iron, you have some of those metals are really hard metals, and there are others like iron or moly with a much lower hardness. So that means inside the mill, you can have powders with a much higher hardness than others. So that means those hard particles act as a ceramic, as a brittle particle in the development of the final particle. So we can consider here the steps similar to the brittle ductile mechanism. We have to mention also additive manufacturing. Despite the number of papers is much lower than the conventional powder metallurgy, we have in the order in this last year, in the order of 20 papers published regarding additive manufacturing. We have to say that most of those papers, maybe the half of them, they use the Cantor alloy. The Cantor alloy, I mentioned before, and there is in the order of 34% of papers in which we have the Cantor alloy, in which we have replaced the Cantor alloy by aluminum in order to tailor the microstructure. And we have also some refractory metals, and we have also some other alloying elements. But most of the works are based on the Cantor alloy. In additive manufacturing, in one pool of typical laser bed pool, we can find in the same part different kind of microstructure, equiaxial grains, small equiaxial grains in the border. We can have random equiaxial grains, but with different sizes, like you can see here on the left and on the right, and even columnar grains. But usually, after the additive manufacturing process, we can follow with an annealing process in which we can tailor the microstructure and get at the end, and to have at the end this kind of equiaxial grains. And in the case of FCC materials, with a lot of clusters of clustering in the microstructure. So let's go to analyze a little bit the mechanical behavior of the hydropialoids. In this graph, we have plot the compression strength against the elongation, against the contraction in percentage. So if you see the dot points, the blue points are the as cast hydropialoids, the ingot metallurgy hydropialoids, and the yellow one are the powder metallurgy hydropialoids. And we have seen that we have this distribution quite similar if we consider more or less the same amount of papers published with the same materials. So you can see that we can find some materials with high level of compression strength and low level of deformation, and even some materials both from ingot metallurgy and from powder metallurgy with high level of compression strength and high level of deformation. If we go a little bit further and we analyze the compositions, here we have most of the transition in this area. We have most of the transition high entropy alloys, and in this horizontal zone area we have the materials, the papers that have used the Cantor alloy. So with the Cantor alloy we have a lot of possibilities to get different kind of properties for different applications. So in this graph we can compare the hardness against the ductility, hardness against ductility in both high entropy alloys produced by ingot metallurgy and high entropy alloys produced by powder metallurgy in orange. As you can see, the ingot metallurgy materials can reach a little bit more level of deformation, despite we can find also some powder metallurgy materials in this area in which we can consider we have reached a high level of deformation. But most of the powder metallurgy materials are concentrated in this area, in which we have even higher levels of hardness, but lower levels of deformation. We can also try to analyze the tensile behavior, but the problem is that we don't have so much papers published with tensile properties. If you see, only these blue dots are from conventional from powder metallurgy, and all the others are from ingot metallurgy. And we have plotted also some other structural alloys. Here we have stainless steels, and here we have ODS steels and intermetallics or Inconel in order to compare. So we can say that also even powder metallurgy materials can compete with these conventional structural alloys. If we separate just the materials obtained by additive manufacturing, here we can see in this area inside the orange circle, materials produced by selective laser melting. The yellow one is electron beam melting, and direct metal melting deposition is this green one. And inside this square, we have the materials developed by the with the Cantor alloy. These are two dots of conventional powder metallurgy, not additive manufacturing. So we can see that we can obtain quite different possibilities in terms of tensile feature and elongation. So the possibilities of hydropialoids in terms of tensile behavior is really interesting, because we can tailor a lot the final properties regarding depending on the manufacturing process. So let's go now to explain some special opportunities for powder metallurgy. Here we have the first one. In powder metallurgy, we can mix powders from different natures. In that case, we have a matrix of aluminum alloy. We mix the powders of the aluminum with powders of hydropialloid, and we can develop a material which is a composite, in fact, in which the reinforcement is the high entropy alloy. So that can give us good or very nice properties in terms of tensile features, elongation, or hardness. Another possibility is the opposite. The high entropy alloy could be used as matrix, and we can use as reinforcement ceramic materials or intermetallics or any others. And doing this way of alloying, which is typical for powder metallurgy, is not possible to do it in another alternative processing method. We can increase the tensile or the hardness, or we can, and sometimes we can increase hardness and the same time an elongation. In that case, we have reduced the elongation, but in this other case, in this area, we can see how we can increase hardness and elongation. Another possibility, of course, is to develop cemented carbides in order to replace cobalt as binder in the conventional hard metal. Here we have, in this color, cemented carbides with cobalt, conventional cemented carbides, and here we have high entropy alloys used as binder, in replacing the cobalt. Here we can see that we have an interesting area in which we can compete with the conventional cemented carbides. This is a topic which is under development, so we can really to develop so much these possibilities in the future. We have plotted here just materials produced with similar processing condition. So these cemented carbides, conventional cemented carbides, has been manufactured by HEAs like the high entropy alloys. Another interesting possibility in the case of the powder metallurgy process is to develop the ODS, oxide dispersive strength materials. This is another interesting field, because by this way we can cover the high temperature applications. And as you see here we have the high entropy alloy, and at room temperature and at 800 degrees testing. And here we have the oxide dispersed high entropy alloy with yttria and titanium oxides. So we see that we improve a lot the stress, the tensile features, without reducing so much, in the case of high temperature, the elongation. So this is another interesting field that could be developed by combining high entropy alloys and powder metallurgy. So as a summary, I'd like to say that potential of powder metallurgy is really vast, and the level of the obtained product is competitive with the conventional high entropies obtained by ingot metallurgy, and also with materials that can compete for the same, let's say, niches or the same areas of applications. PM represents an easy way to obtain special materials. We have mentioned composites, cemented carbides, and so. So here we have a field in which is a material that is impossible to be obtained by alternatives. We have a lot of potential opportunities to produce the so-called different high entropy alloys, just in terms of alloying elements. PM even can be considered more competitive than traditional materials for the high entropy alloys in some specific application. But of course, we have to do a lot of work in order to provide to the market reasons to use powder metallurgy instead of other processing routes to develop the high entropy alloys or to develop these new materials. And just to finish, the time was really short. We didn't have time to talk so much about these possibilities, but there will be another talk regarding high entropy alloys, in that case focusing it on high temperature applications and the opportunities for powder metallurgy in this case, or for high temperature applications, in one special interest seminar in the session regarding the functional materials for high temperature application. And if you are interested on this topic, there will be another talk in this seminar, in this special interest seminar, and you can attend it if you have interest on that. Thank you very much, and I will wait for your questions in the future. Thank you.